Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our today's video, our focus will be on the properties estimation, and in this lecture, we will solve or we will calculate various physical properties which are very important once we are talking about any industrial chemical process. So in today's lecture coverage, we will be using the book Chemical Engineering Design, Coulson and Richardson's Chemical Engineering Series, 6th edition by Ray Sinnott and Kevin Dollar, and we will solve different examples for the properties estimation. So let's go to the example 8.1 of this book, and that example states that calculate the density of a mixture of methanol and water at 20 degrees centigrade with the composition of this mixture as 40% weight by weight methanol. So it means the remaining 60% will be water. We have been given that the density of water at 20 degrees centigrade is 998.2 kg per cubic meter, while the density of methanol at the same temperature is 791.2 kg per cubic meter. So let's assume that, or let's take the basis of 1000 kg. To calculate the volume of water, we need to multiply. Now this is kg, which is 1000. And in this 1000, if we assume that is the total amount, 60% amount is of water, while 40% amount is of methanol. So this is kg, but obviously it is not completely 1000 of water, but 60% of this 1000. So 1000 multiplied by zero point 0.6, so it will be 600. So 600 kg will be of water and 400 kg will be of methanol. The first thing of it. Now we have to calculate the volume. So kg over kg per cubic meter will give us the volume. So for this we have divided it by the density of water at 20 degrees centigrade, which was given to us as 998.2. So we get 0.601 cubic meter. Same way, we will calculate the volume of methanol. So first we will multiply 1000 by zero point 0.4 to ensure that we are calculating the quantity related to methanol only. Then we will divide it by the density, which is 791.2 at 20 degrees centigrade. So we get the volume of methanol as 0.506. Now, since both species are involved in the process, so we will calculate the combined value of volume, and how we can do it by simply just adding up these two values. So 0.601 plus 0.506 will give us the answer of 1.107 cubic meter. Now, if we want to calculate the density of the mixture, this is the volume of the mixture. We have assumed the total mass. So mass divided by volume will give us the answer of density, and that is 903.3 kg per cubic meter. So this is how we can calculate the density, or this is one of the method which is reported in literature to calculate the density. Now we need to find the percentage error. So experimental value is 934.5 kg per cubic meter for this mixture at 20 degrees centigrade with this composition. So if we have to calculate the errors, it is 934.5, which is the experimental value, minus the calculated value, which is 903.3, divided by 903.3. So the difference is, or the percentage error is 3%, which would be acceptable for most engineering purposes. So this is our first example in which we have studied how we can calculate the density of a mixture. Going to example number 8.4, and now we will calculate or estimate the thermal conductivity of benzene at 30 degrees centigrade. We will use this formula, which is K thermal conductivity is equal to 3.56 into 10 raised to power minus 5 Cp, which is the specific heat capacity, bracket rho raised to power 4, rho is the density, divided by m, which is molecular weight or molecular mass, whole raised to power 1 by 3. Now we have been given that the density of this benzene at 30 degrees centigrade is 875 kg per cubic meter. The molecular mass is 78, while the specific heat capacity is 1.75 kilojoule per kg degree centigrade. So we will just substitute the value here. Cp replaced by 1.75. The value of rho is 875. M is 78. So we get the value of K from this expression as 0.12 watt per meter degree centigrade, while the experimentally calculated value is 0.16, and if we calculate the percentage error, it is 25%. Again, solving another example of thermal conductivity, but this time for the ethane at 1 bar and 450 degrees centigrade. And now the formula is a bit different, so we are using different formulas. And K is equal to mu, which is viscosity, bracket Cp, which is the specific heat capacity, plus 10.4 divided by m. M is the molecular weight or molar mass. So for ethane, the molecular weight or the molar mass is 30 C2H6. Accordingly, we calculate it as 30. The value of Cp is given as 2.47 kilojoule per kg degree centigrade, while the value of mu is 0.0134 millinewton second per square meter. So accordingly, we get the value of K as 0.038 watt per meter degree centigrade. The experimentally calculated value is 0.043 watt per meter degree centigrade, and the error is 12%. Now you can see these two errors are a bit high, but obviously there are other methods reported in the literature, so we will see which method gives us the closest answer, and then we can use that method. But again, this is just one of the examples which we are solving to calculate different properties. Now we will go to this example number 8.6, and we will estimate the specific heat capacity of urea, which is CH4N2O. So there are four components involved in it: carbon, hydrogen, nitrogen, and oxygen. Accordingly, if you look at this table for each element and for supplement phase, it has provided us the value of the heat capacities for each element. Like for carbon, if it is a solid, it is 7.5 joule per mole per degree centigrade. But if it's in liquid state, it is 11.7. Similarly, for all the components, it is given carbon, hydrogen, boron, silicon, oxygen, and so on. But if you see carbon, hydrogen, and oxygen, these values are given. But for nitrogen, the value is not given. So we will use this all other term to calculate this specific heat capacity. How we can do it? First, we have to write down the elements: carbon, hydrogen, nitrogen, and oxygen, their molecular masses. For carbon, it is 12. For hydrogen, it is 4. Now, for single hydrogen, it is 1. But since it is multiplied by 4, so accordingly, it will be 4. For single nitrogen, obviously, it is 14. But since there are two nitrogen parts involved in it, so it will be multiplied by 2, and accordingly, we get 28. For oxygen, it is 16. Sum of all these will give us a total molecular mass of 60. Now you see only one carbon element is involved. So accordingly, and it is a solid system, urea is a solid. So we will use this table or this column. So for carbon, it is 7.5. For hydrogen, since four are involved in the system, four hydrogen components are, or four hydrogen atoms are involved in the system. So accordingly, 4 into 9.6, we get answer of 38.4. For nitrogen, as I have said that there is no information of nitrogen over here, but accordingly choosing all others, we can select 26. So 2 multiplied by 26 will give an answer of 52. For oxygen, 1. So 1 into 16.7, it is 16.7. So once we sum all of these, the overall heat capacity of this mixture or the urea is 114.6 joule per mole degree centigrade. If you want to convert it into the mass units, we have to simply divide by the molar mass, and we can get 1.91 joule per gram degree centigrade or kilojoule per kg degree centigrade. And the experimentally calculated value is 1.34 kilojoule per kg degree centigrade with a percentage error a bit high, which is 43%. So again, just I have said in the previous part that we need to find different ways of calculating it, and the closest way to the experimental will be our suitable method. So these are the different examples which we have taken from this book to calculate or to estimate the various properties. And I hope that through this lecture you will be able to calculate the various properties for mixtures or for your system of interest. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video, and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.